Digital communication originally functioned like a warehouse, shipping one box at a time. The system loaded a single parcel, moved it across the belt, and stopped until a confirmation stamp returned from the other side. Because the hardware was forced to wait for that return signal before loading the next packet, the network remained idle for most of its operational life. The infrastructure existed, but the channel was barely being used. To solve this, engineers developed the sliding window protocol. It grants the sender permission to keep a specific number of unacknowledged packets in transit simultaneously. This shift changed the logic of the network. Instead of a series of stop and start deliveries, data transfer became a task of active stream management. The system functions through a set of strict numerical boundaries. On the sender side, the send window size, or SWS, dictates the maximum number of packets allowed on the wire at once. Last frame sent minus last acknowledgement received must remain below the window size. Arriving ACKs slide the bracket forward, admitting new packets. The receiver's window size defines accepted sequence numbers. These cycle around a rotating dial, preventing the confusion of old and new packets. These mathematical brackets ensure that both machines stay synchronized, regardless of the distance between them. If a packet is lost in transit, the sender relies on a retransmission timer. If the clock runs out before an acknowledgement returns, the system triggers a recovery sequence. Go back N requires receivers to accept packets in perfect sequence. If packet 1 is missing, packets 2 and 3 are discarded. Once the timer expires, the sender goes back to the failure point, retransmitting the lost packet and every subsequent packet again. In selective repeat, the receiver buffers out-of-order data, holding packets 2 and 3. This saves bandwidth, as the sender only retransmits the specific lost packet to fill the gap. However, selective repeat requires a larger sequence number space. To avoid ambiguity between new data and retransmissions, the range of available numbers must be at least twice the size of the window. Go back N keeps the receiver logic simple, but risks wasting bandwidth on duplicate transfers. Selective repeat maximizes bandwidth, but requires more memory and a larger sequence space to track the data. Reliable delivery also depends on the receiver's ability to process data. If the receiving application is slower than the incoming stream, the buffer will fill to capacity. To prevent an overflow, the receiver advertises a smaller window size. This forces the sender to reduce its transmission rate until the receiver clears its buffer. In a zero-window state, the receiver halts all incoming traffic. The sender stops and waits, occasionally sending tiny probe packets to check if the receiver has reopened its window. This feedback loop keeps the sender and receiver synchronized, ensuring a high-capacity server does not overwhelm a device with limited memory. Beyond the endpoints, thousands of different data streams share the same public routers. When these paths become crowded, packets are dropped due to congestion. Senders manage this through a congestion window. In slow start, transmission speed doubles every round trip until an error. Following a drop, the protocol shifts to a sawtooth pattern, increasing speed linearly but cutting it in half when congestion occurs. The final speed of any connection is a constant negotiation between the receiver's local storage and the global network's congestion limits. To reach maximum efficiency, engineers must determine exactly how many packets are needed to fill the physical path. This is the bandwidth delay product, the total volume of data in flight across a connection's round-trip distance. Maximum throughput is achieved when the data window matches this volume. When the window fills the pipe, the sender transmits continuously without pausing. Tuning this window is what allows high-speed data to move across massive distances, such as satellite links, without wasting available capacity. This architecture is the core of TCP, the protocol that carries the majority of the world's web traffic. Every time a browser connects to a server, it uses a three-way handshake to negotiate window sizes and scale factors before the first byte of a web page is sent. This logic also powers modern variations like QUIC, as well as the wireless layers that manage data over cellular and Wi-Fi connections. Maintaining this performance requires the sender and receiver to dedicate memory specifically for unacknowledged and out-of-order data. The functionality of the web rests on these mathematical brackets. Billions of them slide every second, incrementing sequence numbers and timing acknowledgements to ensure every pixel and text string arrives in order.